So hello, good morning all of you. Today we are going to discuss about identities in lattice. So yesterday we have seen about the what is meant by polynomials. So in this lecture we are going to discuss about identities in lattice and also inequalities in lattice, and also there are some three theorems in my lecture. So first of all we discuss about the what are the identities in the lattice. So I will first of all write the definition of identities in the lattice. The identities in the lattice are of the form P equal to Q, and if we have to define inequality, it is of the form P less than or equal to Q. First, and P and Q are the polynomials. We have a latticeal, and in that lattice, if we have defined identity in lattice, then this is the identity where P and Q are polynomials, and for inequality, P is less than or equal to Q. So this is identity, and this is inequality in a lattice. And we have this identity. This identity is equivalent to the two inequalities. What are these two inequalities? These two inequalities we have. So it is like that. Two sets are equal, A and B, if and only if A is a subset of B and B is a subset of A. So this identity is equivalent to these two inequalities. So I hope that you might get the concept of identities and inequalities. Identity means equal, and this is less than or equal to for inequality. So this is about the identities in the lattice and inequalities in the lattice.
But what is meant by this inequality? P is less than or equal to Q means what? When we will say that P is less than or equal to Q? Huh?
It's a polynomial P.
But when it will, after substituting, you should get that value.
Value evaluated at some point.
So you explain that. When we say that P is less than or equal to Q, if this is a polynomial,
meet Q is equal to P.
No, that is fine. But that is, one is polynomial, the other one is polynomial, right? So when we say that it is less than or equal to other, after substituting, you take any. If it is a polynomials in n variables, then you take any n tuple,
yes.
a0 a1 up to an minus 1. Then P of a0 up to an minus 1 should be less than or equal to Q of a0 up to an minus 1. Yes or no?
This polynomials आता आपल्या पॉलिनॉमियल्स असतात एक स्क्वेअर काहीतरी तशा अल्जेब्रिक झाले. इकडे पॉलिनॉमियल्स असतात इन टर्म्स ऑफ मीट अँड टर्म. सो ह्या पॉलिनॉमियल इव्हॅल्युएट करायच्या. इव्हॅल्युएटेड आर लेस दॅन ऑर इक्वल टू. Yes. And yesterday we have seen the polynomials in the lattice. So based on that we have a theorem, that is the polynomials in the lattice are the isotones. So we will discuss that theorem. So you know that what are the isotones. So first of all I will write the statement of that theorem. Polynomials functions are isotones. So this is theory statement. If we write, we have to write mathematically. If a0 is less than or equal to b0, a1 is less than or equal to b1, up to a n minus 1 is less than or equal to bn minus 1, then
ये result है ना? उसका वाला पहले रिजल्ट्स क्या है?
कौन सा?
ये रिजल्ट्स आप प्रिपेयर नहीं किया क्या? नहीं ये क्या है? ये प्रूव नहीं किया क्या?
ये स्टेटमेंट है ना सर.
उसका प्रूफ है ना?
हाँ, आइडेंटिटीज इन लैटिस. हाँ,
तो वो स्टेटमेंट क्या लिख रहे बाद में? वो
पॉलिनॉमियल्स फंक्शंस आर आइसोटोन्स. वही लिख रहा हूँ.
ओके.
So polynomial functions are isotones. So you have know that isotones, if a is less than or equal to b, if and it is under the mapping sum of phi, then phi of a is less than or equal to phi of b. So here we have proved that polynomials in the lattices are isotones. So if we have this, then the polynomial polynomial evaluated at this points is less than or equal to this. And moreover, we have some general statement. Some variable, if we take a variable, suppose
x naught.
x naught meet x1 to xn minus 1. This is less than or equal to. Here we have taken meet, so here we will join. So this is polynomial is bounded between them. So this is the statement of our theorem. So first of all, understand it. Polynomials are isotones. So this is the statement we have to prove this. So we will prove it by using mathematical induction on the rank of polynomials.
One second. So this isotone means that whenever ai's are less than or equal to bi's, polynomial evaluated at ai's is less than or equal to polynomial evaluated at bi's. And not only that, you take any polynomial p, it is always has this relation. This is also polynomial, namely meet of all xi's. The other side is a join of all xi's. So any polynomial, given any polynomial, you have a one left bound and right bound. And this is true for any polynomial p. Is this clear? Yes or no?
So we will prove it by using mathematical induction on the rank of polynomial. So you know that the mathematical induction, first of all we will prove it holds for the rank 1, and then we will assume it holds for the rank of a polynomial having a rank k, and then we will prove it holds for k plus 1. So by mathematical induction this result will be hold. So we will prove it. So first of all we consider a polynomial p having rank 1, that is it is a monomial. So first of all rank of some, we are taking the polynomial p, consider its rank is 1. So it will be some xi, some x, it is monomial, some variable only one. So if we take a polynomial, some let polynomial evaluated at these points, it will be some ai for so as we are taking rank 1,
goes right, p is equal to xi for some I, there I. Then you remove this I less than or n, it is not necessary there.
So for a0 to up to an,
then it is obviously ai only, na? For that same I.
So as we are taking for rank 1, it is monomial. So we have it will be only one value. Similarly, if we take a bi, then what will be its polynomial p of b0, b1 to bn minus 1. So but in the statement we have that a0 is less than or equal to b0, a1 is less than or equal to a1. So we have ai less than or equal to bi. So what we can conclude, p0 p of a0 up to this is less than or equal to this. So we can write
one, so go slow. You left side you write ai is less than or equal to bi, implies just in that same line, ai is less than or equal to bi. This is given to us. This implies p of a naught ai is less than or equal to p of b naught up to bn minus. Is this clear?
So for the polynomial having rank 1, we have proved that the results holds, that is polynomials having rank 1 are isotones. So we will assume that the polynomials having the rank k are also isotones. So
leave it. You write here and write there. After that erase.
Okay.
Board hai na, both bada board hai.
So we will take a rank some polynomial q having rank
less than or equal to
k. So assume
less than or equal to k. You write
yes, less than or equal to k. For this, assume for this our result hold. Now we will prove for polynomial having rank k plus 1. Suppose take a polynomial p having rank.
Go slow, little slow. Don't hurry. What is meaning of this one?
So
just let them tell. Yes. So if you have any polynomial whose rank is less than or equal to k, then for that polynomial this condition is true. Is that clear? Now we will prove for any polynomial whose rank is k plus 1 is also true, right?
So let us take the polynomial having rank k plus 1. Suppose the rank of polynomial p is k plus 1. So we will divide some polynomial p it as a q meet r. Suppose this is the polynomial having rank k plus 1, and these are this is found by using these two polynomials meet. So these two are also polynomials, but you have to take in mind that these polynomials are of the rank less than or equal to k, because if one of them is k, other should be 1. So
right. You write because you erase that less than or equal to k. It has different meaning. This you can write as either meet. Also, you write in bracket r in bracket r o r r r r o r. Either you write anything as meet or join because it's a polynomial, where you write where rank of q and rank of r are less than or equal to k. Is that clear? Rank of those two polynomials. So this we have already seen in last class also. Given any rank, polynomial of rank k plus 1, we can write as either meet of join of two polynomials whose rank is less than or equal to k. Is that clear? So that we can apply the assumption for this q and r, polynomial q and polynomial r. Yes.
So now we have taken this. Now we have to prove that this for the polynomial having rank k plus 1, this holds. Yes, na? So you have one general statement that if a is less than or equal to b, if and only if a meet b is equal to a. Yes, na? So we will for this we will use that general statement. Now if I take meet of these two polynomials and show that the meet is this, so obviously this will be less than or equal to this.
It is not a polynomial now because you are substituting.
Yes, yes.
It is a value belongs to lattice. Is that clear? It is not a polynomial. P of a naught
yes,
equal
yes,
to
it
n
is
minus 1 is a value.
Value put केलेली sir. x0 च्या जागी a0. So we will take the meet of these two and we will show that this will hold. So we will take some p of so what is our p? It is meet of these two polynomials. So we will split it as
Write only a naught a n minus 1, b naught b n minus 1. Skip b1.
Similarly for in terms of b's. B n minus 1. It is n minus 1. So we have taken this. Now you can observe that q is a polynomial of having rank less than or equal to k, and we have assumed that the results holds for that k. So let us observe these two terms. So we are taking by assumption what we have these this will be only this.
Because this is less than or equal to
this
value.
and we are taking meet. So what should be this combination? ह्या दोन्हींची मिळून ही टर्म येणार आहे फक्त. तर मग इक्वल टू आपण त्याला इकडे लिहू शकतो. तर इकडे लिहू नंतर तिला, आणि ह्या दोन्हीचं तसंच r is a polynomial having rank less than or equal to k. So we are taking this meet and this is also less than or equal to this, and so we will write this term this, and for these two and for these two we have this term. So what we have left only these two terms are left, and what that is q of a0 up to an meet with r0. So now what is this? This is a p. Yes. So what we have proved that it is equal to, we can write directly.
Right here. Go slow. Don't write step by step.
Okay, sir. So what we have?
Is the step clear? Why everyone? Why we got that? Because Q of AIs is less than or equal to Q of BIs, and R of AI is less than or equal to R of BIs, right?
So we have that P is equal to Q join R. So we can write here it as a P0 of A n minus 1. That is, the combination of these two is equal to this. So we can write P of A0 So the results holds for polynomial having rank k plus 1. So it also holds for any rank. So we have shown that polynomials are isotones, and there is one extra statement. Moreover, we have some join. The polynomial is bounded by these two. So we will prove that statement. So what? हे तर लक्षात आलं ना isotons. So we will prove that general form. Now if we have some variables such that some now we are taking the meet of some elements. So it should be always less than some one of the elements, and this should be
not one of the element. It is true for every I.
Yes. म्हणजे आपण म्हणजे काहीतरी एलिमेंट घ्यायचो आणि त्यांचा मीट घ्यायलो, मग ते एखादा एलिमेंट पेक्षा जनरल मध्ये लहानच असते.
This x0 x1 up to xn minus 1 is less than or equal to each xi. Okay, so right for all, and this is less than or equal to what?
For join them.
Join of all those xi's.
So now consider it as whole term as some x and some this as a some y. Now so what will we some have x equal to xi less than or equal to y. Now if we put values x value in this, so we have the polynomial some x 2x and this is the monomial in only one variable. This is also, so what will be one it is only in one variable, so we have
One
x.
second, you in between you have written wrong. P of x1 x2 xi. See that left hand side x is less than or equal to x1, okay, also less than or equal to x2 and so on, right? So what we have proved, ai, if a1 is less than or equal to b1, a2 is less than or equal to b2 and so on, then p of that ais is less than or equal to p of those bi's. Yes or no? So p of this x n minus 1 times. So here you will have p of x0 x1 up to xn minus 1.
Yes.
That in between is polynomial p of x0 x1 up to xn minus 1. Is that clear?
Yes.
This you erase that xi. It is not clear. Is this clear? Whatever we have proved just now, from that it is following, right? There we have written for values. Here we are directly saying for polynomial relation, right?
So we have x is less than or equal to
it is y only, p of y.
Yes. And what is our x? This is our meet of these elements, and y is join of these elements. So it will hold.
Why p of x is x?
It is a monomial.
Huh? Because whatever polynomial expression is there, you are substituting in each xi the same value. Yes or no? So whether it may be meet or join, what you will get is only that one expression.
समजा आपली एखादी पॉलिनॉमियल काहीतरी तीन व्हेरिएबल समजा x1 x2 x3 यांचा मीट जॉइन घ्या आणि x1 x2 मध्ये x3 घ्या, x च पुट करा, मीट घ्या जॉइन घ्या, शेवटी फायनल x च येणार आहे. त्याच्यामुळे p of x is x. Similarly for y, so it is our x y, when we put the result will hold. So this is the final statement x0.
If you are not understanding someone, you ask. Any problem?
So this is our the theorem that the polynomials are the isotones, and moreover we have the this general form. So this theorem is proved. If you have doubt some, so there is a next theorem about the identities in the lattice. So we will prove that result. So I have told that what are the identities that in latticeal, if two polynomials p equal to q, these p equal to q, then this is served as a identity. Now the next theorem. Now if let be the identities in the latticeal, समजा. For this, there exists only single identity. We are taking some identity pi equal to qi in lattice. Then there exists a single identity p equal to q, such that for all pi equal to qi holds in latticeal, if and only if p equal to q also holds in latticeal. So this is the theorem of our statement that some identities p is equal to q.
So basically it is very simple. If you have suppose 4-5 identities are given, using that you can get actually one single identity. With that single identity, all this will be true. Similarly, if you have an identity, okay, which contains more, then you will have also, that means if p is equal to q, from that also you can derive pi is equal to qi. Okay, so given when you have n number of identities, from that n identities you can form one single identity, okay, which satisfies this all identities. Is that clear? So if you have p1 is equal to q1 and p2 is equal to q2, we will get a new identity p is equal to q, where p1 is equal to q1 also comes, p2 is equal to q2 also comes from that single identity. Is this clear? How will
So in first part we will prove that there exists a single identity p is equal to q in latticeal, and in the converse part we will make use of this p is equal to q in latticeal, and we will prove it holds for some identities pi is equal to qi. So first of all we prove there exists a single identity p is equal to q in the latticeal. So we have this pi is equal to qi. So for I equal to 0, 1, we have p0 equal to q0 and p1 equal to q1, and let suppose pi and qi be the some n array polynomials. N array polynomials. No, now we will take these two polynomials as a combination. Let's it denote it as n, such that so we are taking combination of this p0 and p1, denote it as some n, some let n. Now we have know that p0 is equal to q0 and p1 is equal to q1. So we are taking it as a equal. So if we now we have P0 of this.
One second. So suppose we use like mathematical induction type. So suppose assume a P naught is equal to Q naught and P1 is equal to Q1. So for these two inequalities, we should get one inequality P is equal to Q such that these conditions are satisfied, right? So basically what is our P is meet of those two and our Q is meet of these two. That is the idea. Are you following?
Yes. So for I is equal to 0 and 1, we have P equal to Q, where our P is this, and it is of the form A0 up to A 2n minus 1.
X, you write X because it is a polynomial in xi variables, right?
Yes, sorry, sir. So you can observe that here are the n variables, here are also n variables, and we are taking mean. So we are proving that for I is equal to 0 and 1, P is equal to Q, where our P is of the form this, and it is denoted by P of x0 up to x 2n minus 1, and so it is equal meet of these two.
Huh? It is actually 2n starting from 0, right? You have here n variables, there you have n variables. In that sum may be same also. Huh? Same also. Sum may be different. There again xi's you write, not ai's. Right hand side. P naught of xi. Not a naught an minus 1, xi's. We are taking a polynomial P as meet of those two polynomials. X naught up to x n minus 1.
Sorry. So for I is equal to 0 and 1, we have P is equal to Q. Now we take in general for this. Now we will assume that A0, A1 to A 2n minus 1 belongs to L. Yes. So what we have actually to prove P is equal to Q. For in we have to prove for 0 equal to 1 in general. We have to prove it. So let us take some points from latticeal. Now we have the polynomials this P of x0 up to x 2n minus 1. So write it as a.
So when you substitute those ai values, what you will get? Equal, right? A naught. So don't confuse, xi's are variables. And whenever you want to find value, you have to take ei's. Is that clear? From L.
So what will be our this? We put here. These are the variables x0 and these are the polynomials evaluated at by putting value in that polynomial for that variable. So, but what we have know that that P0 is equal to Q0 and P1 equal to Q1. So, here we can write Q0 of this. But what is our polynomial? This is our Q of x0 up to x2.
It follows. That is what we are checking, right?
P equal to from those when inequalities in case na P equal to double integral P is less than equal to P is greater than equal to. तो जब हम P1 equal to P1 में अलग इक्वालिटी में P1 less than equal to P1
No, you see, it is about equalities. If you have Pi is equal to Qi's, P1 is equal to Q1, P2 is equal to Q2, like suppose you have n equalities. From that n equalities, question is, can we get one single equality which whenever this is true, they will also true, and whenever they are true, you have one relation which is also true, right?
equal है इसमें होगा क्या वो inequalities P और P equal to Q होंगे.
But it is for P is equal to Q only we are proving, right? P is equal to Q only we are proving. Now, there is no question of inequality here. We are actually proving equal.
एक को कर गया तो हो गया अलग-अलग इक्वालिटी के लिए वो inequalities में लिखना सर.
We don't require that. What I am saying, you are directly proving equal. See, P is equal to Q if you want to prove for two polynomials. You don't need to prove P less than or equal to Q and Q less than or equal to P. It is enough if you prove that P evaluated at any point is equal to Q evaluated at that point. Is that clear? So he started saying P equal to Q if P is less than or equal to and Q less than or equal to P. But that is not necessary. I mean, you can directly prove that P evaluated at any point. If it is equal to Q evaluated at any point, then P and Q are equal. When you say that two functions f and g are equal, if f of x is equal to g of x for every x, yes or no? So same thing here also. You don't need to go to inequalities, right?
So we have this statement and we have that q combination this is equal to this. So we can write for u0 up to a0 up to a 2n minus 1. So meet q0, meet q1. So we have p equal to q for in general. So we have proved that p is equal to q in lattice L holds. There is this single identity. Now we will.
So 1 second. So what you have observed here, if you take pi is equal, p naught is equal to q naught, p1 is equal to q1. Two equalities we have taken, two identities. Then we got one identity, single identity, p is equal to q. If pi's and q's are in n array polynomials, then what we got p and q, they are 2n array polynomials. Are you following? You can see that we have taken a naught, a1 up to a 2n minus 1 belongs to L, right? So if you have 3 p naught is equal to q naught, p1 is equal to q1 and p2 is equal to q2. So from that what you obviously expect, your p will be in 3n array variables. Is this clear? Similarly q will be in 3n array variables, so that you get that equation, identity, right?
So now we will take use of that that there is a single identity p is equal to q in lattice L, and we will prove for pi equal to qi.
So even though we proved for p naught is equal to q naught, you can prove it for any finitely many n also, right?
So for proving that convex part, we have to take some assumptions. Consider that x0 is equal to a0, it has a a1 up to xn minus 1, it has a n minus 1, and from variables further this we are considering they are equal. This is assumptions. So and these all values are equal of taking their joins such that a join, and let us consider this value as a. So our each
1 second. What he is trying to prove is, suppose take p is equal to q. Okay. Now how pi is equal to qi follows, right? That means p and q are polynomials in 2n variables. Yes or no? So we take the particular values and we prove that pi is equal to qi. Is this clear? And those are our xi's. Xi's up to xn minus 1. You take A naught A1 up to AN. Before that step you write let before that step you write let above just above that let A naught comma A1 up to AN minus 1 belongs to L. And for these AIs, we want to prove that Pi of AIs is equal to Qi of AIs. Is this clear? Yes or no? Using the identity P is equal to Q, right? But P and Q are in 2n minus 1 in 2n variables, right? So we have to take some other values using only those UIs. So we are taking x naught is same as A naught, x1 is same as A1, up to xn minus 1 is same as An minus. And after that you simply take their join of all those elements. Is this clear? Now substitute these values in P is equal to Q and you see whether you get P1 is equal to Q1 or not. Nice.
Okay. So these are A0 up to An minus 1. So each AI should be less than or equal to A. This will be, and what is I? Our I running from 0 to n minus 1. So we will take polynomial for this, that such that which is taken P0. So we are taking polynomial. So this is a fixed value, that is a monomial. So we have this value it as a. So we can here also write, and for this a we can here also write 0 P1. So this is P0. We are applying polynomial. So P0 of AI, what are our AI? 0 to A minus 1, and for this single value we have P0 of this, and what will be value? Only A, and this is also for that polynomial. So we have P0 of this is equal to P1 of A up to P1 of AAA, and for yes, so what we have? P0 of A0 up to A1 An minus 1 is less than or equal to P1 of A up to A. So we have this formula from this is equal to K and A equal to this, so less than or equal to this. So, and now we have the result that A is less than or equal to B if and only if A meet B is equal to A. Now we have this A is less than or equal to A. Yes, let that A is less than or equal to B. This, if we take meet of these two, we will get this. So we will now take that. So we have taken now.
That is same as what? This is equal to, because it is less than or equal to, so P naught of that is equal to meet of these two. Meet of these two is what? Meet of these two is that itself, na?
Yes.
Right there. Okay. This is equal to P naught of A naught up to An minus 1. That left side equality you remove. Remove that. Right
yes,
implies.
Okay, or this. So now we have know that this P is equal to Q holds in L. So we will put this so P is equal to Q holds in L. So we will take P0 it has Q0.
What is left hand side? What is P naught of that meet P1 of that? Because your P is equal to what? Your P is equal to P naught meet P1. Yes or no? So therefore this is same as, one second, this is same as what? P of that values. Yes or no? But we know P is equal to Q. So therefore P of that all values is same as Q of those values. Right? But Q is Q naught meet Q1. Are you following? So we are using P is equal to Q, right? And P is P1, P naught meet P1, Q is Q naught meet Q1. Right?
So we have these. So and what will be their meet? It will be this only q0.
Because whatever we have proved for p naught above, same way you can conclude for q naught is less than or equal to q1. Yes or no?
So here we have considered that there exists a single identity p is equal to q in L, and we have proved for that q0 is equal to p0. Similarly for we can q1 equal to p1. So this is our the theorem. Or
remember we have proved for two equalities. When you have two equalities, how we can get a single equality? Suppose you have n equalities, n identities. What is your p? Meet of those n identities, meet of those pi's. Yes or no? So your p is equal to p1 meet p2 up to pn. Our q is equal to q1 meet up to qn. Is this clear? Which one? Here? Here. So this is basically what we are using. We already known. What is known is p is equal to q. And where our p is what? p1 meet q1. This is p naught meet p1, and our q is q naught meet q1. Okay. So whatever you have p naught meet p1 is same as q naught meet q1, because we have assumed that p is equal to q. Yes or no? And whatever we have proved here, that p naught of this one is less than or equal to this, same thing you can apply for q naught, right? So what you get here is, if you write this you will get less than or equal to. So therefore q naught meet of q1 is same as q naught. So you are getting q naught meet q1. This is same as q naught. So we have proved that q naught is equal to p naught when we have considered p is equal to q. And this proof you can prove it for q1 is equal to p1 also, right? So if you take given any n identities, this we have understood for two identities. P naught is equal to q naught, p1 is equal to q1. We got a identity p equal to q. What is p? Is obviously in terms of pi's, and q is in terms of qi's. Simply take meet of this and your q is meet of that one. Are you following? And we proved that whenever p is equal to q, pi's is equal to qi's, right?
So there we have proved this. There is also next theorem, that is identities are preserved under sublattice, homomorphic image and ideals. So we will prove that theorem, that the identities are preserved under. So you have know that preserve means राखून ठेवणे, समथिंग इज आपल्या जपून ठेवायचं असते. आता काय आयडेंटिटीज, सपोज लॅटिस येईल आपला आणि त्याच्यात आयडेंटिटी p इज इक्वल टू q. आता ही याच्यात आहे समजा इन लॅटिस एल मध्ये. आता ही आपल्याला प्रिझर्व करायची सब लॅटिस मध्ये, होमोमॉर्फिक इमेज आणि आयडियल मध्ये प्रिझर्व करायची, म्हणजे ती त्याच्यात पण असू शकते. म्हणजे सपोज यू टेक अ L1 as a sublattice, this identity also holds here. If we take homomorphic image phi from lattice L to K, this also holds in K. So under homomorphic image, and if we take ideal, it will also hold in that. So whatever identity we have in that lattice, it is also in sublattice, homomorphic image and ideal. So it is preserving under these three elements. So we will prove that theorem.
Preserve means it holds there also. If you have an identity is true there, then it also true there. Okay.
So first of all, I will write the statement. Identities are preserved under
ऐसे लिखते क्या कोई? हाँ? छोटा बच्चे जैसे लिख रहे हो, हाँ? समझ में नहीं आता क्या कैसे लिखना है? हाँ? ऐसे पहले 3 नीचे वाला लिखते हैं हाँ?
इधर हाथ आना. So let us take identity P is equal to Q holds in L. So we will prove for it is also true in sublattice. So let
But
us
that
take
is obvious, right? It is very obvious
Yes.
statement. You don't need to prove. What is meant by P is equal to Q in L? You take any, suppose they are n array polynomial. You take any n elements from L, it satisfies. And if it is a sublattice, those elements are actually from L only, right? That is trivial.
okay.
You give exercise. Huh?
Yes, exercise for.
Take exercise.
So what we have to prove, it is also true in homomorphic image. So let us take phi be a homomorphism from this be a onto homomorphism. So we have to show that P is equal to, we have know that the P is equal to Q in L, we have to show that P equal to Q also holds in K under this homomorphic image.
So when you say onto, that is same as saying, right, K is equal to phi of L, right?
Yes, yes.
K is equal to phi of L.
म्हणजे
दो बार क्यों लिख रहे? कोई तो ये दोनों सेम है ना?
K is equal to phi of L.
तो ये निकाल दो ना, पहले वाला निकाल दो. हाँ. Okay.
So now this is onto homomorphism. Let us take some points from K. Let us see it as a B0, B1 up to Bn minus 1 belonging to K. So at this is onto homomorphism, there exists.
1 second, go slow. Why we are taking points from K? Because we want to show that identity holds in K. So take any n minus 1 elements, n elements there, and prove that identity, whatever P is equal to Q, okay, also holds in K. That means P of Bi's is equal to Q of Bi's. Is this clear? Haan.
So there exist points in L. Such that under this homomorphic image, it will be this.
Is that clear? Yeah.
This, now we take what we have to prove, that P is equal to Q also holds in K. Now we will take polynomial.
What is phi of B0, B1, B2, Bn minus 1? हाँ, आपका जैसा टाइम लेना है.
So we take now we have that P is equal to Q holds in L. So we will write here. Now for this polynomial P, exist L madle आहेत elements A, and we have given that P is equal to Q. So now we will take elements from the K. So what we have, that B should be written as a homomorphic image under phi. So we will write here as a P of, what should be B0, it should be phi of A0. So we have this. Now here we can interchange this phi and P. Let us understand through म्हणजे आता आपण काय करू शकतो तिथं phi of P of this म्हणजे असं लिहू शकतो. तर ते कसं लिहू शकतो ते ठीक आहे. So how this can be interchanged? Let us understand it as a simple example. Suppose we have a polynomial such that x naught meet with x2. Suppose we take this, now we evaluate this polynomial under this phi of A2. We will put this, it will what become?
Wait, what you are writing? Yeah, comma, you write comma. Phi of A0, comma,
So here we can write phi of A0 join with A1.
Why we can write that?
Phi is a homomorphism.
So basically, because of phi is a homomorphism, you can take phi outside, right? Yes.
So here also we have phi of A0 join A1.
Yes, yes. Okay, correct. Meet A2.
And what is this? This is a polynomial under P.
P of A0, A1, A2.
So this you see that
Comma,
P of
comma.
this
You write
phi of
comma
0.
there. A0, comma A1, comma A2. Not join. A0,
हाँ,
comma join निकाल दो. हाँ. अरे don't confuse. Yeah, na, this is phi of A0, A1. This is simply phi of A0, A1, right? So P of phi of this AIs is phi of P of AIs, right?
So we will interchange here. It will be P of A0 up to A n minus 1. And what we have know that P is equal to Q holds in L. And so we will P is equal to Q.
You close one more bracket right side. One more bracket is there, na?
So we have this.
Again you take phi inside.
Yes, now we can interchange. Q of phi of A0 up to phi of A n minus 1. And what is phi of A0? It will be Bi respective changes. If A will A0.
Udari, you write that one step, which is same as what?
Q of B0 up to B n minus 1. So what we have proved that P is equal to Q. Also holds in homomorphic image, under homomorphic image. So what is remain? Ideal. So we will prove ideal. So we will prove it for the ideal. Suppose let it will be idea of L. It will be ideal of the lattice. And consider some variables such that x0 xn minus 1 belongs to that d of n. So this yes. So these are the variables belonging to our ideal. So we can have p polynomials. These we have these polynomials also belongs to our ideal. Similarly for q. And what we have to show that our claim is P is equal to Q for that ideal. So claim, we can write here claim as P is equal to Q for idea of L. So we will prove this. So first of all, we have in under homomorphic image we have here I have shown that phi and p can interchange. Here also there is one short understanding. We will also here prove that what is that short understanding. If we take a
just 1 second. This is small correction here. There it is a ideal lattice. So this is ideal lattice means elements are ideals there. So these are all not variables. Okay, so you take I0, I1 up to In. Just like there B0, B1 we have taken, right? So these are elements are nothing but this. Now we want to show that P of, when you substitute these things, P of I0 up to In minus 1, whatever you get, that is same as Q of I0 up to In. And it is an ideal. Okay, so what you have here is I0, I1 up to In minus 1. Right? So what you have here is the ideals means ideal lattice. Okay. So we have a lattice containing elements are ideals. So there we prove that it preserves. That means P is equal to Q, then P of this ideals is equal to Q of ideals, right?
So here also we some understand. If we have a polynomial some x0, it will be x2. If we take it as a P of I0, I1, I2, what we have? It will be as a I0 join I1 meet with I2 and also
Yes. So here our values what we are going to substitute, they are, our elements are nothing but ideals. That is what he is explaining there. Your polynomial is a variable, your polynomial is x0, x1, x2, join and meet. Then when you substitute I0, I1 and I2, what you get is that right side expression, which is again an ideal. Is this clear?
now we know, here we know that I join or yes, I meet J. This is equal to the, it is smallest element generated by intersection of these two ideals. So now and we have yesterday we have seen that that H, it is of the form H naught up to H n minus 1. We take element A belonging to H and this if and only if condition here. Now A belonging to H and this is the yes. So we will have A less than or equal to H naught, yes, join up to H n minus 1. So we have this.
This is not square bracket, it is
yes.
one side it is open and
is
the other
closed.
side it is closed. It is an ideal, smallest ideal containing that H, right?
Now we will take some, it is A belonging to this I intersection J. So it is also,
You write one side open and the side closed.
This is also for if A belonging to, but this is belonging to this, if and only if this belongs to this. A belong to I0 join I1 meet with I2. So we have this statement 9.
That is only example. Why you are writing that there? That is why you are writing.
For this we can also write here A is less than or equal to small I intersection with small j. No, meet of small I and small j, where small I belonging to capital I and small j belonging to capital J. So
what you are saying? You are saying that there is an element in that ideal. Okay. That means it is less than or equal to some element.
Yes, I meet J. Yes, this element.
So that A is less than or equal to, right? Next step, A is less than, that is belongs to only. You write that belongs to. Next, if and only if A is less than or equal to small I0, I1, I0 join I1 meet I2, small letters. But that is same as polynomial evaluated at small I0, I1, I2, right? That equal to Nietzsche.
This polynomial evaluated at this A
X, you use X, okay, no problem. P of small I0, small I1, I2. P of one second. Let me explain that. See here, take this example. Okay, this is an example. You are understanding by an example. So you take something here. Okay, suppose some variable. x is here if and only if x belongs to here, right? So x belongs to this polynomial I0, I1, I2 if and only if that x is here, right? But when we say that that isn't this ideal, if and only if that x is less than or equal to, okay, x is less than or equal to some element here, some element here, some element here. So that means I0 join I1 meet with I2. Is this clear? But this is same as what? This x is less than or equal to, this is nothing but the polynomial evaluated at I0, I1, I2. Polynomial evaluated at I0,
Yes.
I1, I2. That means x is here if and only if as x is less than or equal to this one. Are you following? Right? Some whatever you take a here, whatever. Okay. We use this result to prove this one. Right?
So we have that if x is belongs to polynomial here, if and only if x is less than or equal to this. So we use this. Now here for this we know that P is equal to Q in latticeal. If x belongs, now here we will write what we have shown that if x belongs to this, if and only if x is less than or equal to polynomial evaluated at that particular point. So
that P of I0, I1, I2, you can use it for Q of I0, I1, I2, right? Yes or no?
So for that for this P we can write Q, that because P is equal to Q holds in our latticeal.
There only you write if and only if next one P of I0, I1, I2 is equal to Q of I0, I1, I2. Yes or no? In general, he is right.
So what this x is equal to P belongs to this if and only if it is less than or equal to Q. So this follows that P is equal to Q also under in ideal lattice.
Little bit confused. That one line I will explain here. From that you take x belongs to P of I0 up to In minus 1. Right? From this what we have observed here is that x is less than or equal to P of some variables you get In minus 1. But this is same as, but because this is same as Q, so x is less than or equal to I0 up to In minus 1. Right? But whatever you have applied for P, that is also true for Q or not. So x is less than or equal to Q of this one is same as saying that x belongs to Q evaluated at those ideals I0 up to In. Right? So we proved that if something is here, then it is also here. That means this is equal to this. Is this clear?
So identities are also preserved in ideal lattice. So we have proved this theorem. So this is all about the lecture. Thank you.